welcome everybody on this third webinar from engineer workshop on servo drives. For the part of you that didn't attend our previous webinars, I'm Adrian Boryło, product leader of Servo and Motion Group. Together with me is Błażej Siudaj, product manager of the same product group. And today we will be speaking about
energy efficiency, energy saving in servo applications.
Yes, exactly. But before we go to that, few organizational things. First, do you hear us? And do you see us?
Please write comment on the chat.
Yes, please write comments if you can see, if you can hear.
Okay,
good. So there is no problem. Great. And the other things, if you will have any question during a webinar, any question that you want to ask us, please write it down on the chat, but with the question mark. Because on the end, we will answer all of these questions, and this question mark will help us to see if this is a question or not. Because of course, if you want to discuss between yourselves on the chat, you are welcome, and you can do it. It is also good. Sometimes on our webinars, there are a very big and deep discussion on the chat. So it is also good to share the knowledge in this way. The second thing, if you want to, after you will hear what you want to show, then you can always sign up on the, let's say, consultation. So as you can see on this top blue bar with the green button check, so how to speed up your machine, we can connect with you and show you how to, I don't know why this is how to speed up your machine.
I was thinking about that.
Yeah, so
we can show you how we can find savings in energy consumption on your machines.
Exactly.
Sorry for that.
Yeah, this is some technical error. So if somebody from our technical team on this webinar is hearing us right now, it is good to change that because we are speaking about the energy efficiency today. So of course you always can sign up and we'll connect with you. We'll show you how to do that in your application on the consultation. Yes, and I think it's all from the organizational thing at this point. We can start. So I will start sharing the presentation. Please give me a moment. Okay, so at this point, you should be able to see the presentation. So, Błażej, we can start, I think.
Yes. Well, Adrian, before we go further to our topic, I'm going to ask you why we even talking about that topic.
So, in recent years, in particular, we have been experiencing an upward trend in the price of electricity. So this directly correlates with the expenses of industrial plants. So the recent increases have had a very negative impact on their financial health.
I agree. While it sounds like general truth, so maybe tell it like it is in numbers.
Gladly do so, because as you can see on this graph, we can already speak of twofold increase compared to the situation before the COVID-19 pandemic. The prices has gone down a little in the last quarter, but definitely we can say that they will never come back to the level before the pandemic.
Why?
I think it will be easier to understand when we look into the second part of the chart. So on this blue line, there are the prices, also excluding taxes as the previous one, but adjusted for inflation. Because a lot of people could say that the increase of electricity prices is only inflation doing, but this is not true. As you can see, blue line part of the graph also goes up because there are also factors like natural resources prices or EU allowances.
EU allowances? What does it mean and how it influences to energy prices?
So another graph, and I will show it to you, that the EU allowances or the EU emission trading scheme are a kind of permit, or more simply, a limit of greenhouse gas emissions. In other words, if you are part of the European Union, in order to emit greenhouse gases legally, you need to pay a tax on it, especially if in your country most of electric energy comes from non-renewable resources. Interestingly, as you can see, energy prices are rising along with EU allowances prices.
Okay. This curve looks very similar like curve of energy prices, but how does it relate to reality?
So is that even if the geopolitical situation remains stable or will be stable in the future, but we are not talking about that, electricity prices in our region will continue to rise. And what is more, the European Union is adding further environmental targets. So it is rather difficult to think of changing this trend. Besides just energy prices, there are also additional, very interesting facts.
Which ones?
For example, the Paris Agreement on carbon neutrality, where countries or union of countries have already declared when they will reach carbon neutrality. For example, China declared it by 2050, and the rest of the world by China declared it by 2060, and the rest of the world of the countries declared it by 2050.
That's it. In fact, that ship has sailed, and whether we want it or not, we must achieve carbon neutrality.
Yes, but that's not only that. So what's more, some companies are even more ambitious, and those at the forefront want to achieve carbon neutrality in as little as 6 or 5 years at this point. So by 2030, those with a more muted response are sticking to times closer to the Paris Agreement.
So we can expect more activity from European legislation.
Yes, but let us also remember that this Paris Agreement does not only apply to these concerns themselves.
What do you mean by this?
I mean that because, according to the Paris Agreement, after analysis and the maximum possible reduction in energy consumption and CO2 generated by the UA, the manufacturer can also count supplier-side reduction as part of its own reduction.
I already understand. So everyone is responsible. So what this really means is that industrial plants, system integrators, machine manufacturers, or component suppliers, such as ourselves, will be confronted with ever increasing expectation with regard to the energy efficiency of manufactured goods, including machines or components, and furthermore, their traceability.
Yeah, that is, in summary, the company building the machine must both know how to design it energy efficiently and how to visualize this data. For this, they will need to use automation components, and these will need to be energy efficient.
All right, but what is it all about? How we can get with it? It's supposed to be about designing energy efficient applications. And here we are talking a few minutes about some distant problems from our daily work. But just to be clear, first question, Adrian. Are these things shown earlier important? Are they an opportunity or maybe a threat?
This is a simple question. Of course, this is an opportunity. Opportunity to reduce energy costs by consciously design energy efficient machines that consumes less energy. To build a competitive edge in the marketplace by designing machines that implement good energy saving practices. And to build your brand as a responsible end user, an informed SI who knows the right energy reduction practice on site, and of course a manufacturer of energy efficient machines.
Okay, so now let's just figure out how to do it.
Okay, so then let's analyze a simple machine. So here on this machine, what I can see at first glance is, firstly, we can of course optimize the powertrain system. Secondly, the transmission system. What's next?
Next one is software, optimization of the duty cycle. Beyond that, it's worth considering other media, such as hydraulic or pneumatic, which, especially the latter, the second one, generate enormous costs that are not apparent at the first glance. But for now, let's get back to our drive system.
Okay, so in the powertrain, we have two important topics: regenerative energy and hardware with high energy efficiency.
I think the second one is clear, but let's explain to everyone what is the regenerative energy. Where does it actually come from?
So regenerative energy is generated by the phenomena of electromagnetic induction. It is induced by changes in the magnetic field. That is, at the moment of braking, the load pulls the rotor, and the rotating rotor generates energy as on this animation. So to sum it up in the most simple terms, the motor becomes a generator.
Okay, so maybe let's show some examples from real life.
Let's go. So the easiest example of the use of regenerative energy from the real life are wind or hydroelectric power plants, where the wind or water drives the blades that drive the rotor, because there is also a generator. So let's say the motor, yes, electric motor. Or the other example, hybrid and electric cars, where we charge the battery during braking.
Yes, very nice examples. But let's focus on our field. It's when the motor actually generates the power. In what kind of typical application?
So when motor is generating the energy, so when it is working in regenerative mode, mostly during braking. So for example, in lifting application, in vertical axis, so when motor travels down. Also in the converting applications, for example, so Unwinding, yes, and a lot very similar application like that. Always when motor is driven, so pulled by the load. The question is how we can use this energy.
Before we move to its result, let's see how it is implemented in most applications.
What do you mean reuse? It is not automatically used or something?
No, unfortunately not. Every typical servo system, and also the inverter, no matter what manufacturer it is, has more or less the same power circuit structure. That is, after the rectifier and smoothing capacitor, we have a braking resistor. And now, in typical servo amplifier, all-in-one solution, all the braking energy is dispatched in the regenerative resistor.
Okay, so we are wasting all of this regenerative energy?
It is safe to say that yes, it's true. So in other words, we have such a rather inexpensive production hall heating.
Well, yes, because the braking energy is dispatched on the resistor as heat, yes. Then how to reuse this energy then?
We need a slightly different servo drive design.
Okay, so that is a system with something akin to a battery, where in the amplifier do we even store this energy then?
Firstly, through a special circuit, we can easily transfer this energy to other amplifiers that need it at the moment. Besides, yes, we can store part of it in capacitors inside of the amplifier.
Okay, so it's like a hybrid car that transfers braking energy and stores it in the battery, yes? But we have the capacitors inside, not the battery.
Yes, but in servo drives, we have additional functionality. We can return the energy to the power grid.
Well, okay, so let's see what energy savings are possible at all. For a solution with a common DC bus then. So firstly, a group of drives with a common DC bus will be 2 and 3 axis amplifiers in all-in-one version, as you can see. By the way, this is quite a unique solution on the market, where we have 2 or 3 power outputs for the drives with a single power connection. Such systems are popular in the machines of many of our customers, from packaging to the printing industry and a lot of more, for example, manipulators. From our analysis and experience, the energy savings in this type of solution will range from 4 to as much as 23%. The second solution in the middle is a special module, which is both an external power supply and energy bank. Up to 10 drives can be connected to this module for 200 or 400 volt supply voltage. This yields a saving of between 3 and 20%, and sometimes, in good application, even up to 50%. And the third group of DC bus system is the DC bus solution, the typical DC bus solution that probably a lot of you already knows. In this system, a maximum of 69 axes can be connected to a single converter with a 3-phase 400 volt power supply, with possible savings of 3 to 20, as with the FRXC, but in some cases even more, up to 50%, as we will show in the moment. In either case, however, the duty cycle is always very important. Because from our experience with various projects, you can say that, for example, Cartesian systems with 2 or 3 axis amplifier, because this is the 2 or 3 axis amplifier are the best for the Cartesian, yes. You need just one amplifier mostly for the whole machine. The energy savings in this system are usually between 4 and 7%, not very much, but this is still quite a small application. For the lift system from the other side, where regenerative energy during the downward movement of the lift is extremely high, these values between 30 and 50% could be easily obtained. But here I will repeat once more. Thanks to the fact that during the downward movement, the servo braking the load generates enough energy that on the next movement, let's say, we can use this reserve from the previous movement.
And finally, a very interesting case, that of converting or printing systems, where drives that hold the tension generate so much energy, and with a common DC bus, we only have to compensate for energy losses or changes in inertia.
This is why you need to drink water. Okay, but after that, could you please explain to me and to our attendants what this exactly means?
Yes. So now what is relevant here? Before we move on the energy recovery in such system, let's look at the general concept of such machines and the solution used in them. But I promised, only briefly.
Oh, I hope so.
In that kind of applications, we can find 2 popular solutions. The first one with pneumatic brake or powder brakes on the unwinding section. You can see schematic example on the drawing. On the winding section, we have the servo motor, and on the unwinding section, you can see the powder brake.
So, okay, Błażej, nice. But what about the energy consumption of such a system?
Good question. It is quite interesting, because standalone powder brake with natural cooling has low energy consumption. You can see it in the data from our catalog. But if we need to cool the powder brake, because cold temperature will be higher than 75 degrees of Celsius, we need to use forced air cooling, what generates a lot of energy consumption from the additional fan. So standalone and natural cooled powder brake from our catalog, for example, ZKB5XN, will need around 52 watt of power, but the version with fan will need more than 13 times more energy.
Okay, so you mean that we are wasting the energy. In natural cooling, maybe not as much, because 50 watts is very low, but with additional fan, this is a lot, yes? So this is not energy saving solution, right?
Right. Let's go to the second option. Second solution is equipped with motor on the both sides, unwinding and winding side. What is crucial, we can recover and return the energy to the servo amplifier. And now you can ask us why we are talking about it. Answer is simply, in case of breaks, we cannot recover the energy. What is more, we still have to supply those units to keep the device working. In case of servo or even inverters, we can return the regenerative energy to the amplifier and transfer it to the other drives. So servo gives us additional possibility of, let's say, reuse the energy. Okay, now we know that we can change our system and build application with energy recuperation. So now let's calculate how much it can save for us. Here we have a simple application running continuously 6 hours a day, 300 shifts a year, so we have some service stop during the working day. We have a winder NIP and unwinder drives, and we know the capacities of these drives. The unwinder and winder have the same capacity. Additionally, we have the option of using FRXC module to build the common DC bus solution for our drive system, so the drives theoretically can exchange the energy. And first option, let's calculate it very simple. The first option, without energy exchange between the drives, that is, without the FRXC module. The unwinder works in regenerative mode, so it does not consume energy, only logical part of the amplifier. It produces it, and we will dissipate it in braking resistor. The NIP consumes around 4 kilowatt hours per year, and the winder around 6 and 6 kilowatt hour per year. So in total we have around 10.6 kilowatt hour per year, and cost comes to around 2,100 euro per year. And when we go to the second option with energy sharing, under the same assumption, the unwinder drive will generate around 10% less energy than winder will consume. So these two drives nearly balance each other energetically, which means that we really only have to pay for the cost of the energy consumed by the NIP drive. In other words, the unwinder will generate around 6 kilowatt hour per year, the winder will consume around 6.6, while the NIP will consume around 4. So in summary, the energy cost will be around 950 euro. Therefore, in case we have a huge saving, we know that these calculations are very raw, but it shows the potential scale of the savings we can make.
Okay, so that's for there. What about real life example? Because you said that this is raw application, raw calculations, so on. Of course, we had some factor that for the losses, but let's go to the real life example, because it is something that we like the most as engineers.
Yes, so our partner had a lot of drives in their machine, but two drives are important for us here, winder and unwinder. Both axes had 3.5 kilowatt of nominal power, all-in-one drives, not connected via DC bus. And our customer called to us because error occurred. They have problem with regenerative power on the unwinder side. What does it mean? Regenerative resistor built in the amplifier was, let's say, too small, in case of power, of course. And it cannot transfer all regenerative power from amplifier and dispatch it as a heat. So in final solution, we had to change regenerative resistor from built-in to external with power 2.6 kilowatt. And even after that, the resistor was really hot. So it was interesting. What's more, when we will calculate it deeply, properly sized motor for continuous application like this should be sized around 80% of nominal torque or nominal power. When we will calculate 80% from 3.5 kilowatt, it will give us around 2.8. That power is transferred from motor to the mechanical side, and we can say it is average power in the cycle. Moreover, the opposite side, unwinding side, we were able to reach, let's say, around 90% of resistor capacity, which was 2.6 kilowatt. So we have lost around 2.3 kilowatt per cycle. And the difference between the effective powers of unwinder and winder section, of course, in that case, it was around half kilowatt. And that loss was dedicated for loss like mechanical friction, gearboxes friction, torque, or other mechanical loss, or even material resistance. And knowledge about that topic can inspire us to remove the external resistor and connect drives via DC bus connection, or even change the drives to DC bus version to share the energy between each other. That solution can transfer previously lost power to the second amplifier and reduce the power consumption by mentioned 2.3 kilowatt. And based on previous calculation, total power loss is almost equal to required winding power. So in the same way, like in our theoretical calculation, the total energy cost of this pair of drives will be not so far away from zero.
Yes, exactly. And that sounds great. But how to know it when you don't have such a big experience in the field as Błażej, for example? You can use our motorizer drive sizing software, which determines the value of saved or consumed energy through the use of multi-axis or DC bus connected amplifiers. It also allows an analysis of the machine cycles to be carried out in order to optimize the operation of the drives and consequently the amount of energy saved. So as I said before, the cycles are very important. Okay, but you don't use only DC bus solution alone, yes, to reduce the energy consumption in your machine. High energy efficiency in the drives is also important, sometimes being a key factor in their energy efficiency or energy efficiency of whole system. But firstly, what is this so-called efficiency? Let's say in simplest terms, the efficiency is the ratio of the power or the energy used to operate a given device to the power that this device is capable of releasing. And a great example is the incandescent lamps, so older light bulbs, yes, they were popular around, I don't know, 10, maybe 15 years ago. So in many cases, they can no longer be found in shops because they have been displaced by LED lamps. I think they're even illegal right now. And why? Because in the case of incandescent lamps, only 5 to 15% of the electrical energy supplied is changed into light. So the other part, this 80% more, is changed into heat. And of course, for the light, we need it to, from the lamps, we need it to get light, not the heat. And this is why the energy efficiency of drives is a key factor in the energy efficiency of whole system. Why? Because by using energy efficient drives, we are able to save up 10 to 30% of the energy we use to drive them. This is particularly noticeable when using servo motors instead of induction asynchronous motors, which especially at low capacity levels have low efficiency, especially compared to servo drives. But in most cases, the motor drives or mechanics are through some kind of power transmission system. Yes, so when you have the motor, we always, in most cases, connect it to some kind of transmission, some kind of gearbox, for example.
Yes, and this system have different efficiencies. We have collected some of these for you, starting with gearboxes. Looking on the data, we can see that the efficiency of the mechanism vary considerably, and in case of typical worm gearbox, the efficiency starts as low as 40. And in the most efficient one, a planetary gearbox, it is around 97–98% of efficiency. We have collected similar data for the power transmission for linear motion in that case, and starting from the most efficient solution, linear motor, which is very close to 100%, and ending with the worst, self-locking trapezoidal screw with efficiency around 40%. So now the question is whether, when talking about the energy efficiency, it is even worth considering low efficiency transmission system. When the resistance take up most of the energy supplied to the drive. And having discussed this question many times, my colleague Adrian and me, we have prepared some interesting calculations actually to show you which mechanism will work best in your machines in case of energy efficiency.
Yes. So we have two examples of the same machine. And this is the two-axis manipulator. In this case, we will talking about the vertical axis. We will be counting different types of mechanics to the data shown on the screen. And of course, we will assume that the same job can be done with different configuration of components and transmission system. And we want to compare what will consume the most energy. So we have the different transmission system, like the belt, like the ball screw, and so on. Here, what is important about this application. So this is typical manipulator. The vertical axis here, we have the stroke of axis 300 millimeters, the load not very big, 10 kilograms, and some movement resistance, because there is also always some resistance, yes, for example, for the friction. The duty cycle is like that. Descent by the full stroke in 2 seconds. Then there is grip releasing action for 1 second, and we are going up. And next we will have standstill delay for about 3 seconds for the next cycle. And the number of cycles in this case is about 8 and 6 cycles per minute. In case of operating time, to shift is 7.5 hours, 200 days per year, 2 years, and in these years we will make more than 3 million cycles. Yes, so yes, a lot. So, and here on the left side you can see the first mechanics. It is the ball screw with the servo drive, of course. Efficiency of the ball screw is about 94%. It is together with 100-watt motor. This is driving the 100-watt motor is driving this ball screw. And for this data, we calculated in the electrical energy consumption for 1 cycle. Then we have for whole of the same energy for whole of the cycles for this
time period.
Yes, time period. And the cost of electrical energy is the average for the European Union in this quarter. From this calculation, we have cost of use energy in 2 years only on the level of 24 about euros. And with this efficiency, 1 and 4 euro is going for the loss, for the friction, for example. The second example on the right side is the belt drive, also with the servo. Of course, bigger motor, the same cycle. The difference is in the efficiency of the belt drive, because it is about 80% for typical units. And with that, we have the cost of working with this application in the level of 12.5 euros, and the costs for the losses 2.5 euro. 3 more belt drive with gearbox. So the same belt drive that before, but we are adding a gearbox. So now the motor is smaller. We are going to a lot smaller motor, 150 watts, because the gearbox has 1:10 ratio. Then with the same cycle, we have about 30 euros of cost of the electricity and 7 euros of losses. And the last mechanism is gradient pinion solution. Here we have pretty good energy efficiency of 90% for the Rag & Pinion, and the calculation is for 1 kilowatt motors. With that, about 11 euros of energy consumption, and for the losses only 10%, so 1 euro. Now just add the gearbox, and for the same application, for the same mechanism, we have a lot smaller motors, and the consumption of the energy is bigger, around 15 euros, and the losses of that about 2 euros. Yes, so this is for these calculations.
In summary, to do the same job, we can use different systems and, interestingly, different drive powers. Very important point here is that although at the first glance a small geared motor would appear to consume less power, the opposite is true, mainly due to the internal resistance, which is further increased our power consumption. Of course, this does not take into account purchase cost, and it may well be that in tiny geared motor will be a great purchase because it will not consume enough energy to cover the price difference in relation to larger drive. Here it also worth stepping back to the calculations for a moment and paying attention to the size of gearbox. In case of our calculations, the gearbox size was selected as small as possible. It is very often forgotten that the gearbox has internal resistance, and here in such example, on the slide you can see a table with the internal resistance of gearbox for a speed 3000 rpm. We have two sizes of gearbox from the range that can be confidently used for this selected drive. Both gearboxes suits us from design point of view. Both will work in proper way. So let's ask ourselves about three important questions. The first one, which one should we choose? Second one, bigger gearbox because lifetime will be longer. And the third question, what about the energy efficiency? So let's see the first from the table, the first gearbox with ratio of 3:1, for example, and answer the first question. How much of the nominal torque of the motor will be taken up by the internal resistance of gearbox? If we will take the motor with 200 watt, for gearbox with ratio 3:1, the size, what we called size 1, will consume 39% of nominal torque, while size called as a second one will consume 59% on loss, in torque loss. And now you are probably wondering what is all about, that we are surely exaggerating something, and it is not true. Unfortunately, it's true. Our experience shows that it is typical aspect, and you can find that kind of problems in many applications. And that aspect is terribly often overlooked during the sizing, which is in the extreme cases that we can observe case the servo to overload because it's not able to achieve the cycle performance, and internal resistance of gearbox is too high.
Yes, it's too high to drive the motor even. Yes.
Yes.
It's a very big problem because now you have to change the gearbox, or in most cases change the motor, yes, or sometimes change the whole system.
Right. And this is the most forgotten with gearbox, that's seemingly change nothing. For example, ratio 1:1. And here is example. For the same 200 watt motor, gearbox sized on the size of motor, the smallest possible, and ratio 1, the internal resistance is so much high, and that can absorb 109% of nominal torque of motor. That is, for application example, we we are about to have an overload error. Therefore, for calculation, it's worth checking what the internal resistance of the gearbox are and adding them in the software. In this way, we will select the servo drive safely, and we will be able to get the energy consumption value for assumed duty cycle the closest to the closest possible to the actual real value. And let us now return to the example, which is in which we show another part of the application of manipulator.
Yes, because we have still horizontal axis here. So in this second example, for the horizontal axis of the same manipulator, there will be some changes because the axis stroke is a lot bigger. It is it is 2 meters. The load is bigger also because we are driven the vertical axis, and it is 30 kilograms, and also bigger movement resistance. The duty cycle, we're making movement of full stroke for 3 seconds. Then we are waiting because there is a vertical axis movement. Then we are going back, and another vertical axis movement for these 3 seconds. The number of cycles in this case is 5 by 5 seconds per minute. Yes. Operation time, we have 2 shifts as before. Yes, and with the number of cycles in 2 years, about 2 minutes cycles. And for this cycle, the servo and the screw, this combination is out of the order because we can't use it due to the speed of the ball screw. Yes? So the speed is excessive, and ball screw are this type of mechanics that have quite a big limitation on the speed. I don't know, 2.5 meters per second is sometimes too much in most cases, too much for the ball screw. Then we have the belt drive and the servo, which we can use. Here, 2 kilowatt motor without gearbox. And I will skip the details because this is very similar calculation. We consumed around 27 euros, and with that, 5 euros around loss goes to the losses. Then we have the same belt, but we are adding the gearbox and with the smaller motor. But now the consumption is about 130 euros in 2 years. And the rack and pinion, as before, here we have the consumption of 20 euros and 2 euros for the losses. And the last example, when you are adding the gearbox to the rack and pinion system, and the consumption of the energy, in case of price, of course, is 70 euros with 11 euros for the losses. So in summary, when the same work was done with different system, but we obtained very different energy consumption values or the prices of energy values, yes, because this is the same for us. And these values and the values in the previous table from the previous axis do not seem large. Yes, 20 euros in 2 years, even 400 euros in 2 years was not a very big value for one axis. But you have to remember, these are values for one drive. If a machine or rather a production line has dozens or hundreds of them, these values, or especially these differences, start to play a huge role.
And let's summarize it. It's not worth to combine servo motors with low efficiency systems. The losses generated will be extremely high. At the design stage, it's worth considering what you want and what will integrate better in the machine. Of course, sometimes motor with gearbox is the best option, but the question is whether this is always the case. It's advisable to choose components with the highest possible efficiency, especially the mechanical parts, mechanical components. And it is always worth performing a system calculation and comparing the results in our software.
Yes, this is true, and especially the last one. Once again, I want to remind you about this green. Yes, this was green top bar with the button. If you want to perform this kind of calculation from the energy point of view, or just the calculation to size the proper size of the motor for your application, please sign up by this form, and we'll contact you and do this calculation for you.
Yes. So it just to get the whole thing together now. To build an energy efficiency machine, we first need to look at the type of application.
Yeah, of course, because we have a lot of application converting LIB or manipulators. There are applications when we have a lot of regenerative energy. There are applications where it is not even worth mentioning, of course, because it will depend on the cycle and the load.
Exactly.
The second thing is to choose the type of the drive. So whether it will be a multi-axis drive or a DC bus system or some other. And after that, we will choose the right mechanical drivetrain and calculate everything in the software with optimization of the movement. So the drives can exchange energy and recover as much as possible from the system. Right now, it's pretty easy, yes, after all of what we have said.
Yes. So we hope that what we have shown today, we shed new light on the sizing of drives, resulting in more energy efficient applications, and those last digits in the energy meters will start to jump more slowly.
Yeah, exactly. Because at the end, this is what we want, to have lower energy prices in our facility.
Yes, exactly.
Okay, this is the end.